Hey pre-calc students, Mrs. Fallon here. I am obviously out today, so I want to give you kind of the lesson in a nutshell with our first day of rational functions. So what we're going to talk about today is mostly just kind of like looking at the rational function, looking at limit behavior, talking about x-intercepts, that kind of thing. So I'm going to walk you through some of the notes, and then I'm going to give you guys some time to work on some practice in class so that you have some stuff to reinforce. So I ask that you watch the video and that you take the notes, because without it, I think it will be pretty confusing. All right, let's go ahead and get started. So on the first one, what we're going to talk about is basically how we can, I guess, talk about these like limits as x approaches a certain number. So if you remember what a rational function is, it's a kind of a graph that has like these pieces, and like they're like, you know, broken apart. And the reason why they're broken is because they have these asymptotes that are in there. And these asymptotes are like kind of like this line, right, that doesn't exist, where the graph doesn't exist. And so what the asymptote does, it kind of breaks the graph at that line, and therefore the graph, you know, is kind of like a gap in it, if you will. So what we're going to look at is the limit as x approaches these gaps. So if you notice, I kind of drew in this asymptote here, and this is at 1, 2, 3, 4, 5. So we call this x equals 5. And the reason I'm calling it x equals is because it's a vertical line. And an equation of a vertical line is x equals. So what we're going to look is what happens to my graph as we get closer to this x equals 5. I'm going to look at it from the left side and then how it looks from the right side of my graph. So we call that the limit as x approaches 5 from the left. And I don't know if you can see, it's a little tight in here, but what this says is 5 with a little minus sign above it means, let's put that down, means from the left side. So what I want you to do is take a look at your asymptote. So I'm going to kind of highlight that in green. So this is our vertical asymptote. And I want you to look at the left side of it. So the left side of it would be, well, if this is our asymptote, then the left side would be over here. What is my function doing? Well, on the left side, my function's pointing up. So we call that positive infinity. So what this says is the limit as x approaches 5 from the left. So as we get closer to 5, as x gets closer and closer to 5, where is my function going? It's going to positive infinity. We can also talk about the limit as x approaches 5 from the right. So this means from the right side. So what I'm getting at there is, again, we're looking at this asymptote, what happens on the left side and the right side. So again, what I'm asking you is this 5 with a little plus after it means from the right. So as x gets closer to this, like from the right side, coming from the right side towards this asymptote, what happens to my function as I get closer to x equals 5? Well, my function is going down. It means it's approaching negative infinity. So those would be what we call our asymptotes around those we call our limits around our asymptotes. This thing, this asymptote, this green line here, is called a vertical asymptote. And so we write it as x equals 5. All right, so that's kind of an introduction to just to limits. All right, so we're also going to talk a lot about domain. And I'm going to talk, I will show you interval notation, but I'm also going to show you set notation. Set notation is really what we're going to use. So honestly, that's kind of what the format that you'll see me use throughout the rest of this unit. So interval notation means, so for domain, of course, it means x's, right? So look at all your x's that exist. Well, here's a little hint. Every rational function, like if I'm looking at all my x's that produce like points, the only time my x value doesn't exist is when I have a gap in my graph. And so that gap occurs at the vertical asymptote. So basically, the only x value that doesn't work in this whole graph is 5. So in interval notation, you would say from negative infinity. All right, sorry about that. So anyways, what I'm looking at is all the values of x except for 5. So in interval notation, it would look like negative infinity to 5. Don't include 5, so put the parenthesis. Or, and then you would say 5 to positive infinity. Again, don't include 5. I mean, that notation's fine, and I'm okay with that, but I prefer what we use as set notation. So you will see me use this. Because it's the same every single time, it's going to say all real numbers, and then all you do is you say x doesn't equal 5. So this notation will always stay the same. It'll always start with like this X and then the bar and then the X and the weird looking E and the funky looking R. And then the exception will always be whatever your vertical asymptote is. So in this case, it's all real numbers except for 5. Your range, you have to look at your graph for your range. So your range is kind of looking at, if you look at it up and down, right? The only values that don't exist in my range are really from like in this region here, right? Every other value for y exists because I have all the numbers above and all the numbers below. So I want to include all the numbers from, and again, you're looking at y's, so from 2 up and all the numbers from 0 down. So I want to go from 2 to infinity. That's 2 up. So I'm going to include 2. So I'm going to put a bracket. And then I want from basically 0 down. So negative infinity to 0. And again, I put the bracket. How you'll see me write it again, set notation. The only difference here is I'm using y's. And I'm just going to write that as an inequality. So this just means less than or equal to 0 or greater than or equal to 2. And that's how you write your range. We're going to do a lot more with this, but I just kind of wanted to give you an introduction. Let's talk a little bit more about limits. And then I'm going to introduce you to something called a hole in your graph. I don't know if you did this in Algebra 2, but we'll kind of get into it in algebra or in pre-calc. All right, so in this one, I didn't give you, I kind of highlighted some of the asymptotes, but I didn't give you like the format for the limits. So I'm going to go ahead and highlight the asymptotes on here. So those are my 2 asymptotes. So there's 2 limits for every one asymptote, one from the left, one from the right. So what I want you to write is the limit as x approaches. So what number is this? It looks like this is at 7, I said. So the limit as x approaches 7 from the left. So you would write limit as x approaches 7 with a little dash next to it, like a negative sign. And then you would say, okay, our function, so I don't know, I'm going to call it f of x, is approaching. So on the left of this vertical asymptote, my function's pointing down. So I'm going to say negative infinity. I'm going to go up here, I'm going to do the same thing. This is the limit as x approaches 7 from the right. So again, I'm still talking about this asymptote here. My function is approaching, and so on the right side, my function's pointing up, so I'm going to say positive infinity. Let's go to our other asymptote. This one is over here. Looks like it's at 21, supposedly. So this is the limit as x approaches 21. Now this is the left side, so I'm going to put a negative or a minus sign. My function, so we'll call it f of x, is approaching positive infinity. So again, on the left of this asymptote, my function's pointing up. On the right of this asymptote, so the limit as x approaches 21 from the right, my function is going down, so it's negative infinity. So on the right side, it's pointing down. So that's how you would do the end. So we call those like our asymptote limits, our vertical asymptote limits. The next thing I want you to notice is there's a gap, there's a hole in your graph. So we call these like discontinuities in our graph. So whether a discontinuity means like it's not a continuous function. In other words, I can't just take my pencil and trace this whole function. There's gaps in my graph. The 2 gaps occur at my vertical asymptotes, but there's also now a gap right here at this hole. So we have to describe the limit as x approaches that hole. So what I'm getting at is, where is this hole occurring? So the hole occurs when x is 16. So I wrote down here, the hole is at 16, too. So that's what this point is. So when you talk about the limits as we approach this like gap, I'm going to say the limit as x approaches 16, and then I want to come from the left side, and then I want to do the limit as x approaches 16 from the right side. So again, for every asymptote, you're going to do 2 limits, and then for every hole, you're going to do 2 limits. So with the hole, though, it's different. Your function isn't going to approach like infinity or negative infinity. It's going to approach a number. So from the left side, what I'm asking you is, my function is, you're looking at the y value here. As x gets closer and closer and closer to 16, what number is y getting closer to? Well, the hole occurs at 16, 2. So the y value that it's getting closer to is 2. And same thing on this side. As it gets closer and closer, if I'm approaching 16 from the right side, the y value is getting closer to 2. Always with a whole, these two numbers should correspond. Like it should be approaching the same value. So again, this is just a different kind of discontinuity. It's a gap in your graph. It's just a hole. Okay, let's do some more. So this time I'm going to kind of have you put it all together, and we're going to look at my entire function. And so I started by giving you an equation this time. So what I'm going to look at is I gave you the function, and we're going to look at what happens at different parts of this function. Okay, so how do you know where the vertical asymptote is? So one of the things I want to make sure that you understand is that the vertical asymptote has to do with the denominator of your graph. So if you set this equal to 0, it equals your vertical asymptote. I'll have you write that down. So if you set this denominator equal to 0, it equals your vertical asymptote. So what that means is if I plug 3 in for x, what happens? So if I plug 3 in for x, I get 2 over 3 minus 3. Well, what is 3 minus 3? It's 0. What's 2 divided by 0? It's undefined. So when something is undefined, that's what it means. It means that there's an asymptote. So this tells me that when x equals 3, the location is some sort of discontinuity. So it's either an asymptote, a vertical asymptote, or it's a hole in my graph. So the easy way to do this is to look at your denominator, set it equal to 0. So x minus 3 equals 0. This is where my discontinuity is going to exist. So it's either going to be a vertical asymptote or it's a hole. How we tell the difference is if it's x equals 3, like it's a vertical line, like x equals a number, it's a vertical asymptote. And I'll show you what it would look like if it's going to be a hole. We'll get to that one next. All right, so what I'm going to do is I'm going to go ahead and graph x equals 3. So I'm going to put in my vertical asymptote. So that's what that looks like, that vertical line. And so what I want us to do now is talk about my limits. So the limit as x approaches my vertical asymptote of 3 from the left, and then the limit as x approaches my vertical asymptote of 3 from the right. All right, we don't have a graph to kind of look at here. So what we're going to look at is we're going to look at what happens algebraically as we get closer and closer and closer to 3. So from the left side, I'm going to pick some numbers that are really close to 3, but not quite 3. So like, for example, I might pick 2.9, and then I might pick 2.99, and then 2.999. And we could keep going on forever, but you'll get the pattern here. So I'm just going to use these 3 numbers. In other words, I'm coming along. I want to know what's happening to my graph. So at 2.9, is my graph going, like, is my graph going to have points that are going to go up, or is it going to have points that are going to go down? So if you grab your calculator, plug 2.9 into this equation. 2 divided by 2.9 minus 3, I get negative 20. If I take 2.99 and plug it in for x, I get negative 200. If I get 2.999 and plug it in for x, I get negative 2,000. You can probably guess what's going to happen next. So what this means, as x gets closer and closer and closer to 3, what happens to my y values? They're getting smaller and smaller and smaller, which means my function is going down. So my function, which is f of x, is approaching negative infinity. So that's how you can kind of tell what's happening around this asymptote. Is if you plug in numbers that get really close to that asymptote, look at what happens. Is it getting really small, or is it getting really big? If it's getting really small, it's going to a negative infinity. If it's getting really big, it's going to positive infinity. Same thing here. If I approach numbers from the right side, so give me numbers that are really close to 3 but not quite 3. Well, if I could do 3.1, 3.01, 3.001, right? Plug all those numbers in for x, and I'll do this part for you. So if I did, I get 20, 200, and 2,000. So again, this means the right side. I'm approaching it from the right side because the numbers are getting closer and closer to 3, but from the right. This one meant from the left side. All right, notice what happens to my y values. As x gets closer and closer to 3, my values are getting bigger and bigger and bigger, which means my limit is going to positive infinity. So this is, without giving a graph, how you can figure out what's happening around your asymptote. What our goal is to be able to figure out how to graph these functions without having to use a calculator. So I'm trying to teach you like some ways in which you can graph these functions without having to like rely on just plugging it into your calculator. Let's do another example. The first thing I want you to do in this one, so this one's a little bit harder. The first thing I want you to do is I want you to factor this equation. So how do you tell whether the undefined x value is a vertical asymptote or a hole? So the first thing I want you to do is factor. I'm going to be honest with you. That's going to be your first step pretty much always. So I'm going to get g of x equals, and on the numerator, I'm going to factor out a GCF. So I'm going to factor out a 2x, and I get x minus 3. On the denominator, I can't really factor it. I just get x minus 3. So here's how you tell if you have a vertical asymptote or a hole in your graph. Do you see how both of this numerator and denominator have a common factor? Do you see how like this has x minus 3, this has x minus 3? When that occurs, this represents a hole in your graph. So a hole equals a common factor in the numerator and denominator. So anytime you have a common factor in the top or bottom, like one on the top, one on the bottom, that's going to be a hole. All right. So once we did this, we're going to reduce this. So what happens here is that like there's a gap. So this is going to cancel out. So really the function I'm graphing is going to look like this. Well, what does this graph look like? This is a linear equation. It's going to be a straight line. But there's a gap in our graph. So what makes it different than a normal linear function is there's a hole. In other words, it's not continuous. There's a gap. We're going to have to jump over it. Okay, so here's how do we know where that hole exists? So, okay, so first, we figured out the hole there because there was a common factor on top and bottom. The other thing I want you to notice is that this denominator, or I'm sorry, that this function now, we're always going to use this function. So this function now is what I'm going to use to graph. It is linear function. There is no vertical asymptote. How do I know? Because the denominator is 1, right? If I set my denominator equal to 0, I'm going to get nothing. I don't have anything. All right, so I know that my hole in my graph is going to exist. So it's going to exist, I'm going to put it down here, when x is 3. So all I did here was take this like common factor and set it equal to 0. I'm going to plug this 3 back into my original equation. So not my original, I'm sorry, into my factored equation. So if I plug 3 back in here, what do I get for my y value? Well, 2 times 3 is 6. That's where the hole is going to occur at the point 3 comma 6. 1, 2, 3, 4, 5, 6. All right, so that means there's going to be a gap in my hole. A gap in my equation. So if I had a linear equation, it's going to come along and there's going to be a gap there. So I drew in my line because I knew that it had a positive slope and it went up. But again, what you could look at is you could say, well, as I get closer and closer to 3, is this function getting smaller or bigger? So again, you could go like this route. Start plugging in numbers that are closer to 3 on the left side. So again, this is left. And then you would notice that my numbers are going to get like 5.8, 5.98, 5.998. What number is this getting closer to? It's getting closer to that y value of 6. So remember what I said about like a hole. It's going to approach your y value. So the limit as x approaches 3 from the left, so as x gets closer to this hole from the left side, my function, my y value, is getting closer to 6. Same thing over here. I could take a look at it from the side. So 3.1, 3.01, 3.001. So as I get closer and closer and closer to this gap, this hole, what happens to my numbers? Do they get bigger or smaller? Well, not even that. What number is it getting close to? It's getting close to 6. So if you were to put those in your calculator, that's what it would look like. So as the limit as x approaches 3 from the right, my function is approaching 6. And so that's how we know how we can get all of our missing pieces of information. All right, the last thing I want to talk about, I'm going to go over basically how to provide, like how to do all of this, all of this information just given an equation. I'm going to do that on a separate video because I don't want this video to be too long. So if you want to try this on your own first, you think you have a pretty good grasp, or maybe you remember it from Algebra 2, I'm going to have you go ahead and try that. And then I'm going to do a video that just kind of goes over these example problems. And then I also have some in-class practice for you guys to be doing. All right, bye for now.